organic chemistry in that green chemistry perspective. In the green chemistry, we have studied the 12 principles of the green chemistry. All the principles are related with the how to perform the green chemistry and how to avoid the hazardous materials and how to replace the solvents, okay, volatile solvents by the green sources. This is all about the green chemistry. Next is a E factor, that is a environmental factor. So it is the indicator of the pollution's effect on the environment and the account of the waste generated in the reactions. Account of waste means what? If we require the desired product, okay, along with the desired product, if byproduct or another material is produced in the relatively in good quantity, then at that time we can say that it is not atom economic. Okay, so at that time we have to focus in the reactions methods in such a way that we will get the maximum quantity and the byproduct, or otherwise we will get the only product, no byproduct. So this will be helpful so as to we will get the environmental benign product. So it is the ratio of the mass of the waste generated in the kg to the mass of the desired product in the kg. So if the mass of the waste is more greater, will be the E factor. Mass of the waste is more, at that time E factor will be the greater, and greater will be the environmental pollutions. So how to calculate the E factor? Here given the one of the example, best example here. For every 44 kg of ethylene oxide, in the reactions, reactant are the ethylene chloroethane 1-ol, and another one reactant is the calcium hydroxides. Okay, if you calculate the weight of the 1 chloroethane ol 8.5, and that is calcium hydroxide is 74, and you will get the product that is oxirane having the weight of 44, and the calcium chloride having the weight of the 111s, and we along with the S2 water. So water is not hazardous. Okay, so required product is our the oxirane. Ethylene oxides is our required product, that is oxirane is our required product. Along with the required product, calcium chloride is the byproduct, that is waste produced in these reactions. So how to calculate the E factor is the mass of the effluent product, means the waste product is the 111, and the mass of the desired product mass is the 44. So if you perform this calculation, you will get the answer 2.54. So the above reaction have the high E factor. Hence this method is not good for the manufacturing of the ethylene oxide according to principle of the green chemistry. So in this way, if we will get the final products and having the greater values, okay, at that time we can say that this reaction is not eco-friendly reactions. When the having the higher value of the E factor, at that time this is not according to the principle of the green chemistry. So in this way we can calculate. Next is the atom economy. So the reaction is said to be the atom economy when the atom of the reactants are incorporated into the desired product, and the percentage atom economy can be calculated as follow. Here the calculation formula is given. Formula for the percentage atom economy is equal to the molecular weight of the desired product into 100 molecular weight of the desired product into the 100 divided by molecular weight of desired product plus molecular weight of the byproduct. So byproduct is also important for deciding the percentage atom economy. For considering this concept, we have the one example. To consider the Diels-Alder reactions. In the Diels-Alder reactions, butadiene and ethene get combines. Okay, cycloaddition reaction takes place, and you will get the cycloproduct. In this reaction, no byproduct is produced. It is a 100% atom economics. How it is calculated? So formula is the percentage atom economy is equal to percentage atom economy is equal to molecular weight of the desired product. So what is the molecular weight of desired product? If you calculate the number of carbon atoms, okay, number of hydrogen atoms, so we will get the molecular weight of the desired products. So one carbon is the 12, 6 carbon is the 12 6 are 32, and total number of hydrogen is the 2 4 6 8 10. Total number of hydrogen atoms is 10. 10 plus 72, that is 82, is the molecular weight of the desired product, divided by molecular weight of desired product is 82 plus molecular weight of the byproduct is 0. No byproduct is here. So multiply by 100. So we will get the 100, means the percentage atom economy of the above reaction is 100%. If any byproduct is produced, so at that time percentage of atom economy will be the below the 100%. It will be 70, 60, 40% at that times. But in case of the pericyclic reactions, all the reactions are the 100% atom economic types of the reactions. So it is good types of the reactions. Next example we can consider here. Consider the acetylation of the aniline using the acetic anhydride as the reactant. So acetic anhydride we have used in the earlier reactions for the protection of the this reaction is the protection of the NH2 groups in the aniline. So this acetic anhydride act on the NH2 groups and block the NH2 group and form the amide types of the linkage. Okay. So here reactant we will get the product, along with we will get the acetic acid. So if you calculate the molecular weight of the acetic acid, which is 60, and the molecular weight of desired product, it is the 135, and perform the percentage atom economy is equal to molecular weight of desired product, it is the 135, divided by molecular weight of the desired product, it is the 735, plus molecular weight of the byproduct, it is a 60. Multiply by 100, means total 135 divided by 135 plus 60 into 100. So we will get the 69.23% atom economic reactions. So as we will get the byproduct, so byproduct reduces, as we will get the byproduct, that byproduct reduces the percentage atom economy. Okay. Byproduct reduces the percentage atom economy of the reactions. Next is the example 3. Consider the dehydrohalogenation of 2-bromo-2-methyl propane in presence of the base to give the 2-methyl propene, to get the 2-methyl propene. So in these reactions we can calculate the percentage of atom economy also. So what is the molecular weight of the products, that will be helpful for us. Okay. So two byproducts are there. One is the ethanol plus sodium bromide, and these two byproducts weight is the 148. Okay, combined weight of this C2H5OH and NaBr. These two are the byproducts. So we have to take addition mass of these two products, that is 46 plus 102 is 148, and desired products is the 56 only. So if you perform the reactions, we will get a 27.45%, which is not atom. Okay, percentage of atom economic is very low, so it's not follow the green chemistry route. Okay, so green synthesis by we are now the performing the green synthesis by using the green methods. In that, we use the green synthesis by using the green starting materials. So glucose is the best example to synthesize the variety of the commodity chemicals using the biochemical pathway. So this route helps to minimize the use of the carcinogenic materials, starting materials such as the benzene. So benzene is the too much carcinogenic in nature. I have told you earlier lecture that cyclobenzene is the cyclohexane or benzene is the carcinogenic in nature used as the solvent. So as possible as we have to be avoid this. So in the reactions we have taken as a catalyst as a biocatalyst. That is E. coli is the biocatalyst. It is the enzymes we use in these reactions. So this is the stereo-specific types of the reaction, stereo-selective types of the reactions. So glucose perform along with the using the coli, that is the enzymes biocatalyst, we will get the 3-hydroxy chemic acid, which is again react with E. coli, we will get the products. And if you reduce this, that is using the reducing agent, that is S2PD, we will get the adipic acid as the products. So this is the green methods. We use the green starting materials. We use the green technique, green catalyst, that is E. coli, and you will get the final product as the glucose. So green synthesis by use. What are the green reagents? So selectively methylation using the dimethyl carbonate in place of the using a methyl halide or dimethyl sulfate, which are toxic to the environment, and dimethyl carbonate is the non-toxic and give the selective methylations. Okay, number of ways to proceed the methylation processes. We perform the Fiddlecraft methylation also. Okay, dimethyl carbonate is also used. Dimethyl carbonate also used. So methyl halide is also used for the methylation reactions. So there are number of ways to perform the methylation reactions, but these methods are the having some hazardous effects, so that we use the green methods. In that dimethyl carbonate we use along with the base potassium carbonate, which is non-toxic and they give the selective methylations. So example, methylation of the aryl acetonitrile. Aryl acetonitrile. So we will get the product. Along with that, we will get the carbon dioxide and the ethyl alcohol. So this is the green methods. Next is the green synthesis by using green solvent. Solvent is also important part. Okay, in the chemical reactions, maximum use, a maximum expenditure, okay, involved in the solvent also. Okay, solvent is the one of the important ingredient in the reactions. If solvent is proper, solvent is the good, solvent is economically friendly, at that times less hazardous product will be formed and less hazardous byproduct will be formed, or less wastage of the that particular solvents. So solvent selection is also one of the most important criteria of the green chemistry. So supercritical carbon dioxide is comes under the green categories, okay, which is liquid CO2 at 31 degrees centigrade, 73 atmospheric pressure, and it is used in the wide variety of the organic reactions. It is used instead of the traditional solvent because this cause the environmental problems, but supercritical carbon dioxide is a non-toxic, non-flammable, renewable and inexpensive. For example, free radical bromination of the toluene in presence of the supercritical carbon dioxide using the N-bromosuccinamide as a brominating agents. So in these reactions we use the supercritical carbon dioxides having the less than 71 degrees centigrade so that we can use it, okay, and we will get the for the bromination reactions we will get the final product, that is CS2Br is the product. So this is the best way, this is the best reactions which promote the green chemistry principles, okay. So in this reaction supercritical carbon dioxide we used as the solvents. So we replace the conventional solvent, hazardous solvent by the green techniques. Next, it is used as a solvent which is the eco-friendly. In lots of the industries applicable supercritical carbon dioxide which is include the polymerizations, essential oil products, productions, coffee, decaffeinations as well as the waste recycling has been successfully carried out. Next is the green catalysis by using the enzymatic catalyst. So enzymatic catalyst is also known as the biocatalyst and it is used in the main industrial organic conversions and hydroxylations of the nicotinic acids. So the reactions using the oxygen for the oxidation reactions, that is the chromo water xylo CNC is the biocatalyst in these reactions. Okay, so stereoselective types of the reactions is another example is the acetoacetate, that is the baker yeast you used. Baker yeast is also one of the easily available, inexpensive, and give the stereoselective product and selectively yield is also high. So next is the synthesis of the nitroaniline, that is the ortho para isolations. So ortho and para nitroaniline can be prepared by reacting the corresponding chloronitrobenzenes 5% ammonia at 170 degrees centigrade and 30 to 40 atmospheric pressure. Simple method of synthesis is the ammonia react with the 170 degrees centigrade along with the 30 to 40 atmospheric pressures and we will get the replacement of the chlorine atoms by using the NH2, means this is the replacement reactions and temperature is also 170 degrees centigrade atmospheric pressure is required in these reactions. On the conversion of the one orthochloronitrobenzene into the orthonitroaniline as the products. In the in the para positions, we can replace the halogen atoms by using the NS3. So we will get the para nitroaniline as the products. So examples are the alternate methods to prepare the para nitroaniline is to be carried out by using acetylations of the aniline followed by the nitrations. Here is the one of the examples. So how to remove the how to form the acetylation products of that particular reaction. So in this reaction is the at the protection groups of the NH2 using the acetic anhydride. So in the first step that is the protections and form the acetylated product. Then we will use the nitrating agents. So in these reactions we have to be carefully observe. This is the NH2 group. Okay, and this NH2 group is the uh, protecting groups and it is the orthopara active groups. Okay, so in these cases what happen, you have to block that NH2 groups by using the protecting agent. This is the protecting agent. So this group is protected means the formation of the here protectant moiety and these protected moieties cannot delocalize the NH nitrogens lone pair of electron. This lone pair of electron involved in this way. Okay. So nitrating agent we use and nitration takes place at the ortho positions. NO2 group is added at ortho positions. Okay. So in this way we stop the NH2 groups and protect the NH2 groups and you will get the final product. So protection is also one of the examples. So if we get the final that is the para positions, so we can add it at the para position also dilute minus along with this dilute H2SO4 and OH minus is a deprotecting group. Deprotecting means firstly we add this group on the NH2 groups Okay, so that nitration reactions easily proceed. And then as we completed the nitration reaction, so we have to remove this group. Okay, we have to remove this group. So for that purpose, removing this group, we have the dilute H2SO4 along with the OH minus. So dilute H2SO4 as act as the deprotecting group, and deprotecting group means it remove the that particular moiety from the NH, and we will get the ammonia as the aniline as the product. So para nitroaniline as the product. So protection and deprotection is also one of the important synthesis is performed. So description is here. Is prepared by sulfonations of the acid aniline into the 4 amino benzene sulfonic acid. It is then nitrated into the N-acetyl 4 amino 3 nitro benzosulfonic acid, which is in acidic medium gives the ortho nitroaniline as the products. So here the number of steps are performed. First the protection, that is the acid we use, then we will use the concentrated H2SO4 for the sulfonation. SO3 is added at the para position. Then we will add the concentrated HNO3 means the agent nano2 group add as the ortho positions, and then ST H plus or OH minus added, we will get the final product at the ortho position. That is the NO2 nitro product as the nitro. Okay, ortho nitro aniline as the final product. So in this way the reaction is performed. So some of the reactions are remaining, that is synthesis of nitrobenzoic acid. Okay, then the parabromobenzoic acid, synthesis of the alcohol. So this remaining reaction we will perform in the next lecture. For if anyone having the not understand this part, only key is the practice. Okay, मैं हमेशा यही